Group of learners conducted an experiment to determine the rate of chemical reaction. They added 12 grams of magnesium powder to 100 centimeter cubed of 0.2 mole um, centimeter cube of diluted hydrochloric acid solution. The balanced equation for the reaction is magnesium, a solid, plus 2 hydrochloric aqua. Product is magnesium chloride. No, magnesium. Yeah, magnesium chloride aqua plus hydrogen gas.
Okay. Thank you so much, Elsie. So a group of learners, they conduct an experiment in order to determine the rate of a chemical reaction. They added 12 grams of magnesium powder to 100 cubic centimeters of a 0.2 mole per cubic decimeter of diluted hydrochloric acid solution. The balanced equation for this reaction is given as follows. All right. Now, the first term says, or rather the first question, we need to define the limiting reagent or a reactant. Well, you know how to define the limiting reagent. Then they say, calculate the number of moles of magnesium that are added. And next they say, which one of these two reactants is the limiting reactant? Justify your answer by means of calculations. And this is actually a 5-mark question. Well, I think they were rather generous in this case because they gave it 8 marks in total. There's no way you can identify the limiting reagent if you don't know the moles for magnesium. Well, they wanted you to pass, all right? So let's go ahead and determine which of those two substances is the limiting reactant. Well, first things first, we need to calculate the number of moles for magnesium. So we know that the number of moles, of course, are defined as the mass divided by the molar mass. So we are given the mass of magnesium, they said it's 12 grams. And the molar mass for magnesium, well, it's just going to be 24. You get it straight from your periodic table. And of course, 12 divided by 24, that is a half. And you know that we don't really appreciate fractions. So you have to write this as a decimal and say, well, we actually have 0.5 moles of magnesium. That was the first question. Now, in the second question, we need to determine which of those two substances is the limiting reactant. And remember, what is the procedure for identifying the limiting reactant? I'm just going to write the chemical equation down here. So we know that we have magnesium which reacts with hydrochloric acid in order to produce magnesium chloride and hydrogen gas. And the balanced chemical equation is by putting these two in front of the acid. Now, the first thing that we need to do is to calculate the number of moles for each of these two reactants. Well, we have already found the moles for magnesium, so now we just need to find the moles for hydrochloric acid. Well, just to show that this is a question in its own caliber, I'm just going to do something like this, right? So it means we just need to find the moles for the acid. But then with regards to the acid, we are given the volume as well as the concentration. So we tell them that the concentration of this acid is defined as the number of moles divided by the volume. Okay, then it's time for us to substitute. Well, the concentration is given to us as 0.2. We are looking for the moles, but the volume is given in an incorrect unit. It's in cubic centimeters. So we need to divide by 1,000 in order to convert this to cubic decimeters. So we get 0.1. And if we cross multiply 0.1 times 0.2, well, we simply get 0.02 moles. All right. Well, I'm just going to forget the unit, but remember to write your unit. And of course, you'll be writing this in the correct sequential steps, right? Yeah, this is on one line. Then on the next line, you're going to put this. And then on the third line, you put that. I'm just writing them like this because I'm trying to save space, to maximize space. You'll do calculus next year and you will learn that we always try to maximize as well as to minimize some things. Well, in this case, I'm maximizing space, all right? Now, we have done the first step, which is to find the moles for both of these reactants. For this one, we had the mass. For this one, the concentration and the volume. Bottom line is we convert whatever it is that we are given to the moles. Right. Now it's time for us to decide. Because what is the meaning of these moles that we got? For magnesium, these are the number of moles that are available at the start of the reaction. It's what we have initially. Sometimes they call them the initial number of moles. Still the same thing, all right? And similarly, this 0.02 moles is what we have that is available at the start of the reaction for this hydrochloric acid. Now we need to know, maybe let's say I want to know how many moles of magnesium do I need in order to react with 0.02 moles of hydrochloric acid. All right? In yesterday's lesson, we found the number of moles that are needed for the reactant that is here. But today, let's find it for the first reactant so that you don't always think it has to be the second reactant that we need to determine. Well, then we tell them we want to know how much of magnesium is needed. All right. Now, how can we find that? By remembering the relationship. Magnesium and hydrochloric acid, they actually relate in a 1:2 ratio. Okay, now I want to know if I have 0.02 moles of hydrochloric acid, then how many moles do I have for magnesium? Well, you remember that you're just going to take this one and divide it by that one and multiply it with that one. So I can choose to put an X here. Well, that's perfectly fine. Well, there's no need to put X anyway. You can just say, well, the answer here is going to be 0.02 divided by 2 multiplied by 1. You can say that. So now you can conclude and say, well, the number of moles of magnesium that are needed in order to react with 0.02 moles of hydrochloric acid will be 0.01. moles. Then after finding the moles of magnesium that are needed, the next step is to compare this number of moles that are available at the start of the reaction, but now we need to compare them with those that are needed. And of course, the moment I say compare, you think of the inequality signs or the equal sign for that matter. All right. Well, let's check. If we look at those that are available, it's 0.5. Okay. But now we only need 0.01. Think of it. We have 0.5, but we only need 0.01. So what we have is greater than what we need. So we'll still have some change, something that is remaining. So what is our conclusion? Our conclusion is magnesium is in excess. It is the excess reagent. But then what is the meaning of magnesium is the excess reagent? It means that hydrochloric acid is the limiting reagent. The question said, determine which one is the limiting reagent or reactant. So you have to tell us in terms of limiting, not in terms of excess. Although it won't be wrong if you said magnesium is the excess reagent. Yeah, it's not wrong, but always try to answer the question according to what they asked you. Over and out. So then, what is the next question? I think you need to see the next question. Well, this one says, hence or otherwise, determine the mass in excess of the other reactant. And this is really a phrase that you're familiar with in mathematics. Hence, the word hence means use what you found previously. But then when they say or otherwise, it means, well, you can choose not to use what you found previously. You can do something that is brand new. So that's really the meaning of that statement. Now, there's one thing that we know about the limiting reagent. If, for instance, they wanted us to calculate the mass of magnesium chloride that is produced, we were definitely going to use the limiting reagent, most definitely, as well as for hydrogen, because we know that the limiting reagent controls the amount of a product that is produced. But in this case, they want us to calculate the mass in excess of the other reactant. Okay? Well, we dealt with a situation like this one yesterday. Because think of it, remember what we said. We said with regards to magnesium, we have 0.5 moles. This is what we have. But we don't need all of this 0.5. We only need 0.01, which means at the end of the reaction, we'll still have magnesium, which is remaining in the reaction mixture. So they want us to calculate the mass of this magnesium that will be left. So then, how do we find that mass? Well, firstly, we need to know how many moles are in excess. And we know that in order for us to find the number of moles in excess, these are equal to the number of moles that we had at the start of the reaction minus the number of moles that were used or the number of moles that were needed. Yes, or the number of moles that reacted. So I'll just use needed, all right? Okay. Well, but then used makes a lot of sense because it's the ones that were used, as well as reacted. Well, reacted makes the most sense, or the mostest. That's the superlative adjective. No, it's wrong. Don't say that in school. Okay. We had 0.5 moles, but we only need 0.01. So which means we actually have 0.49 moles that are in excess. All right. Then now it's time for us to find the mass. Well, we know that the number of moles equals mass divided by the molar mass. Yeah, I have a very terrible capital M. I tried to fix it, but seems like I'm not winning. So if you see something funny in the denominator, just try not to laugh. All right. Well, the molar mass of magnesium, we know that it's 24. And if we now times this by 24, well, we simply find that the remaining mass will be 11.76 grams. This is the mass in excess.
In order to determine the reaction rate, learners measure the volume of hydrogen gas produced per unit time. The results obtained are shown on the graph below.
Okay, thank you so much, Elsie. So in order to determine the reaction rate, the rate of a reaction, learners measure the volume of hydrogen gas produced per unit time. Because that's how we define the rate of a reaction anyway. It's the rate, it's the speed, it's how fast a chemical reaction takes place. But then actually, you can define it in terms of the number of moles, the concentration, the volume. So if you define it in the case of volume, you say it is the amount of volume that is produced per unit time. So remember, you are in the lab, you're conducting an experiment. So maybe you want to track the progress of the reaction in intervals of 5 seconds, maybe. You want to see every 5 seconds how much is being produced. So yes. Well, if we look at this graph, we can see that the volume is actually increasing. But then it's not just increasing, it's increasing at a decreasing rate. I think if you did physical science in grade 10, and on your equations of motions, like on the graphs of motions, I think you should have dealt with graphs that are the same, or the same graphs that I'm talking about, whereby you have something that is increasing at an increasing rate as well as at a decreasing rate. Well, that's what we are having here. It shows that, well, the volume is going to be produced. It increases, but then while it is increasing, well, the rate itself, the gradient is actually decreasing, which shows that at some stage, there won't be any volume that is being produced anymore, increasing at a decreasing rate. And as a matter of fact, you can see that the point X there is the maximum volume that is being produced. No volume is produced above X. Okay. Now we have the times T1, T2, as well as T3. Now what is important here is on the time T1, the volume is still increasing. Of course, it's increasing at a decreasing rate, but it's still increasing. The reaction is still taking place. But then at T2, There is no volume that is being produced anymore. The reaction stops at T2. Why? Because from T2 to T3, the graph is now a horizontal line. And of course, you did maths, you know that if a line is horizontal, it means you have the same y value throughout. Yeah, and the y value in this case is the volume. So the volume is the same at any time that you can have. So it's not being produced anymore. So the reaction stops at T2, not at T3. Be very, very careful of that. It's a trick. Okay? Well, they say define 1 mole of a substance. You can easily do that. And now they say at what time does the reaction reach completion? And if you look at those times, you see an or. It's very important to see an or because it means you have to choose one time. So it's just going to be T2. Yes. Then the last question says, calculate the numerical value of X. In other words, the maximum amount of hydrogen gas, that is being produced. And then they say use 24 cubic decimeters per mole as the molar volume of hydrogen gas. Remember I told you this. Your molar gas volume will not always be 22.4. It changes depending on the mood of the examiner. So always check which one the examiner is specifying. Okay, fine. We know that the numerical value of X, that's actually the volume. So we need to calculate the volume, but then we are given the molar gas volume, which means we need to know the moles of hydrogen gas. And there's also something I want you to be aware of. X is in cubic centimeters, which means if you leave your answer in terms of cubic decimeters, you may not get all the marks. So it's very, very important. Take your X to cubic centimeters. Well, it's easy. We know that it's still the same reaction. So we just need to calculate the number of moles of hydrogen gas. It's very easy to do that. So how do we do that? Well, first things first. We know that hydrochloric acid is the limiting reagent, and we have to use the limiting reagent in order to get the number of moles of hydrogen gas. So these are the number of moles that we need to use. But then we don't just use them blindingly, no. We need to look at our stoichiometric ratios. Well, what is the relationship between hydrochloric acid and hydrogen gas? Well, they actually relate in a 2:1 ratio. But then we know that with regards to hydrochloric acid, well, we have 0.02 moles. So we just need to find the moles for this hydrogen gas. Well, that's going to be 0.02 divided by 2 and multiplied by 1. So this means the number of moles of hydrogen that are actually produced will simply be 0.01 moles. Right. Now that we know the moles, then it's very easy to find the volume because we know that the number of moles equals volume divided by the molar gas volume. So then we have 0.01 here, which is set equal to V. And our molar volume is given to us as 24. Then when we cross multiply, we find that our volume is actually 0.24, but it's in cubic decimeters. So now we need to convert this to centimeter cubed by multiplying this with 1,000. So when we multiply this with 1,000, we find that 240 cubic centimeters of hydrogen gas were actually produced.